Okay, so let's start today's exercise. Please, if I may have some faces. Yes, thanks. This one, far. Okay, so today is about policy gradient methods. So we will focus directly on policy instead of having to go through value functions. So as always, we will have a certain break somewhere in the middle, but today I want to deal with basically three different algorithms. The first part of today's exercise, we're going to see a brief recap of what policy gradient means and how can we construct some parameterized policies. In this particular case, we will use softmax policies. And we will start with a very simple algorithm, which is called reinforce, which is actor only, in the sense that we will only deal with the policy. We will forget about value function in a sense. And then we will reintroduce the value function, which will allow us to be more efficient with some bootstrapping. And this will be called actor critic. And then the second part, we will deal with the notion of a national gradient, and we will see how we can actually improve the standard gradient descent with the notion of trying to select the most natural direction of increase instead of following the gradient in a dumber way. Okay, so to start, I would just want, we will again deal with cart poll, just to have some common background. And I just want to give a very small recap of what we learned the last time. So cart poll as an environment is just a cart with an inverted pole over it. And our task is to balance the pole on its head, so it's an unstable position, and we can only move the cart left and right, so we have only two actions. The state is defined by the four physical quantities of position and velocity of the cart, angle of the pole, and the velocity of the tip of the pole. And with these four quantities define the state, we should be able to find a policy of left and right, which allows us to more or less indefinitely stabilize the pole. Last time, if you remember, we discovered a few things. We discovered that there was a simple but rather intelligent state aggregation, which just said that instead of having to deal with R to the 4 state, we just needed 6 different regions. So if we take a state and we reduce it to 6 different aggregated states, then we had all information necessary to achieve a almost optimal policy. And this was done in this nice work, which we will deal again, this nice, let's say, article, which I have all the references are in the past exercise. Also recall that when dealing with state aggregation, actually it's very simple in the sense that we can forget that we are doing value approximation and doing state aggregation outside the algorithm. So what we will do is that we will take the state from the environment, which is given by this 4-dimensional real vector. We will actually, outside, we will transform into just these 6 regions and use that as a state for the reinforcement learning. Okay, this will simplify a bit the notation, but please remember what we're actually doing some value approximation in between. So outside of the reinforcement learning algorithm, we will take the S and we will transform into the feature vectors, And then we will use the fixture vectors in the algorithm as if they were the state S. Okay. For the algorithm, it's the same in the sense that he has a discrete state. Clearly, I mean, we are dealing with a value approximation. So the possibility of achieving the best performance, it's separated by this. But for the algorithm to work, technically, it's sufficient to do outside the state aggregation. Not all state aggregation are created equal. This smart choice was very simple. It was done by binning in the 4 dimensions. The first binning is that we have absolutely no interest in the position of the card. So whatever S1 is, it will always end up in the same region. Whatever the velocity of the card is, it will not, the region will not depend. And the angle are divided in 3 different regions. One region is that the angle of the card is less than 0, so it's leaning left, and it's larger in the sense that it's less than this value 0.03, which has been found by empirical way. The second region is that the angle is small, and we don't even care if it's small leaning to the left or leaning to the right. And and the third region if the angle is large and leaning to the right. Okay, and then the last binning was that we divided the states into depending on the velocity of the tip of the pole, which is essentially a proxy for the angular velocity. And we divided it by 2. One is that it's the velocity is less than 0, so the tip is moving left or the tip is moving right. So in total, we had this 4-dimensional real vector, and now we have only 6 regions. Okay, and if you remember, we achieved that with this simple function here. So recall that this environment is one of this gym library, and then with these simple 2 lines we are already creating it. Okay. This is the function which aggregates the state. Usually it was very general, but we're going to use it with a specific meaning. Just take the state, with our case, the 4-dimensional real space, and then we take the kind of binning and how many bins you want in the 4 directions. And at the end, it returns with 3 values. And we will see what they are right now. Okay, so just to introduce the simpler notation we are using today. So S is the state, so the environment is going to reset, so we have this state. And then this function is going to give us 3 objects. The first one, xi, is the one we will use. And it's going to be just an index which tells us whether we are in the 1st, 2nd, 3rd, 4th, 5th, or 6th region. The second one is x, which is in a sense the proper vector of features. So it's a vector with everywhere 0 and only 1 where we are, which is the true vector of features, because the vector of features has the dimensions of x, and then x index was what we used the last time. So, for example, the result for a random state generated in the environment was this 4 numbers. So this was the position of the card, velocity of the card, angle, and velocity of the tip of the pole. The binning itself gives us this vector of features. Okay, I have 4 binnings, so I have a 4-dimensional matrix. The binning was that we are in the first bin for the 1st dimension, we have only 1. The first bin for the 2nd dimension, we have only 1. We have in the second, 0, 1, bin in the 3rd dimension, we had 3. And we are in the first bin of 2 in the 4th dimension. So the proper vector of features, what is properly defined in the theory of value approximation, is this. 0, 0, 1, 0, 0, 0, okay? And we will use as an input for the algorithm the ID of this vector or feature. So essentially, we're gonna use the number which is this is the third one. So we're going to use 0, 1, 2, 3, 4, 5. So we will going to use 2. Okay, but it means that we have at the end we had the state which was 4 real numbers. Now we have just one integer which goes from 0 to 5 or 1 to 6. Say. Okay, just to check whether the smart policy was actually working, because we will always try to achieve the same one. So this is, we will, now I will claim that it works, but we never tried to put it to the test. The empirical policy is defined by hand in this way. The reason is very simple. So if the angle theta it's negative, it's very large. So if I'm leaning too much to the left, I want to push the cart to the left to put it upright. Okay, so this means if theta is too close to the left, then my action is it's too tilted to the left. Then I want also the cart to go to the left, and these are the two actions. Because I don't care about the velocity of the tip. If it's negative or positive, I don't care. I just want to stabilize the angle. If the angle is small, here in the middle, I have two cases. If I angle it small, but the tip is moving left, I want also the cart to move left, because otherwise it will fall over. And if the angle is small, but the tip is moving right, I want also the cart to move right, okay? And then if the angle, so the pole is too much tilted on the right, I just want to move to the right. This is the definition of the policy, which you can find also on this paper here somewhere. I apologize, here, okay? I put it hard-coded, just that we know that we work. Then I do 500 episodes. It's the same as always. This is the binning as defined. Basically, these two do not matter. This is the binning in the angle, and this is the binning in the velocity of the tip. This is how many regions there are in all four coordinates. And I do the episode. So this will do a lot of time, and we've done a lot of time. So I just do a cycle over the episode. I just take the state, I do the aggregation, and then I'm taking the optimal policy, and I'm taking the one which I selected as an action in the state X, and I do it over and over and over and over and over and over for 500 times. And what you can see, I just need to remember that I need to, yes, I know. There was a reason I already sent them going, because they take some time. But anyway, in 500 episodes, you can see that actually this time, all 500 times, they went up to the time horizon. Okay, so it means it's very stable. Other times I found that one or twice they fall, because still it's not a perfect state aggregation, so it's still not perfect. But anyway, so this is what we want to achieve with all other methods, and so we want to arrive to this policy. And first of all, this is the main point. So today we are going to focus on the policy and not on the value itself. The value will be used to get to a policy, but our point is that we want a class of methods with a direct focus on the policy. Because, okay, so far we managed to do model-free control, but we had to construct some policies parameterized to the value. Now we want something else. So now we are going to do, instead of going that we had a value and we constructed the policy over the value, we want to have a policy which lives by itself, and it lives by itself with some parameters theta. Okay, so instead of having to go, we had some parameters w, which creates a value approximation, and with that value approximation we create the policy. Now we have some parameters theta, and we have that our policy is parameterized only on that. And we will write like this. It means that this is the policy of being in the state S and giving the probability of doing the action A, while we are parameterized with theta. Okay, there is this convention with the parameters for the value are w, and the parameters for the policy are always theta. So remember, every time we're talking about theta, we're talking about how our policy is parameterized. Now, the idea is still the same as always. We are going to try to get the best policy, so the best parameters which create the best policy, and our ultimate goal is still the same as always, which is to maximize the discounted reward. So our aim, our ultimate goal is to find a way to optimize and maximize this. This is the expected value of the discounted sum of the infinite reward, infinite sum of discounted reward. So now we have to understand how to connect directly the policy with this ultimate goal. So the questions, which are essentially the same question, is how does this ultimate goal depend numerically analytically, mathematically on the policy? How does it depend, therefore, on the parameters theta, which essentially boil down to the question, can I calculate the gradient of this value g with respect to the parameters theta? So if the model is known, one can try to go, since then g can be written, the discounted reward can be written as a function of transition, of reward, of probabilities, and everything is known. One can try and go in a mathematical approach with integrals and try to find a solution, a closed solution there. But that is always a bit complex and needs a perfect knowledge of a model. Fortunately, there is a way to calculate this gradient even in the case of model 3, where we are going to go now. So the policy gradient method, in its most simple form, says that we can calculate this gradient, and we just need the expected value of this term here. So even if we don't know the model, if we collect trajectories and we are able to evaluate this quantity here, if this where the state are being taken with a correct probability given the trajectories, and the action are taken with a correct probability of for the policy, then if I do this, if I am able to do this expected value, then this gives me the gradient of the goal. Okay. Then, as always, when we have some kind of writing like this with an expected value, we can try to do it with proper sampling. So we can create some estimation of this Q value and find from the trajectory the values of the gradient and follow it. Okay. So essentially, at any time, we're going to create trajectories with time t which grows, and then at each time t, we will have some way of finding out what is the value, our estimation of the value q at that time t. We will have a probability of having taken that action, it being in that state, given our parameters. We will be able to make this derivative in terms of theta of this term log pi, And this will give us numerically each time the direction of the gradient, an estimation on one piece of the gradient of the goal. Okay, this seems extremely complex and extremely abstract in a sense, but actually this line here is as a very simple message. Okay, remember, we are trying to do one thing. We have a maximum goal, an ultimate goal, which is the expected future reward with discount. Okay, so how well I am performing, and I'm asking, how can I change the parameters to change this ultimate goal, our performance? And the solution says you have two pieces. The second piece is that you have to change the parameters in a way that somehow change the probability of having taken that action. Okay, since the policy is parameterized by theta, the second part tells us in a way what is the direction I need to change the theta to increase or decrease the probability of taking that action, broadly speaking. And the first term tells us, was that action good or no? This is the value of having taken the action. So in a very, very naive sense, this term says that the gradient is given by how to change the policy depending on the theta. This is the second term. And then when I found out the policy change about the theta, should I go in one direction? Should I go in the other direction? Should I increase the probability? Should I decrease the probability? This is given in a broad sense by the first term, which says this was a good move, this was a bad move. Okay, so broadly speaking, all this policy gradient, if one would like to explain it to without mathematical details, it's just that it tells us the gradient is how to change the policy, and you find it with a second term. Should I change it increasing the probability? Should I change it decreasing the probability? This is given by the first term, which is the quality of the action I took. Okay? So this is what I put here. Okay, this is the two terms, how the policy depends on the parameters and how well I think the policy is currently performing. Whenever we see something like this, we know that we have different formulation and different ways to estimate and approximate this value function Q. Okay, and the different ways I'm going to do this will determine the different kind of methods that there are in policy gradient. Okay, today we will deal with basic ideas from two of them. One is the actor only, in the sense that the estimator will be from a Monte Carlo estimator. So we will not need to compute and store value approximation or value estimation. We will deal only with the reward we get in each episode. And the second part, which is the actor critic, we will have a part of the algorithm which is called the critic, which will be deal separately with the problem of the value evaluation. Okay. Do you have a question so far? Okay. Please, if you do, always ask, always interrupt. Otherwise, so now we have, I don't go deep in the theory, as you can see, but we have this policy gradient theorem, which says that we have a way to update our parameters, which is given by this formulation here. And now we want to find a way to estimate this for this term here. And to change the parameterized policy. So the first thing one should ask is, okay, what kind of parameterized policies are we talking of? Okay, how can we construct parameterized policy pi of A of S theta? So, very simple one, which you have found in we already in the past lectures. and we will use throughout this today, is this kind of softmax policy. So it's a tabular way of representing the policy. That is to say that for each couple of state action, we have one single parameter, which is a theta SA. Then, whenever I need the policy on a state, I just take this formula here, which is say, okay, if I want to know what is the probability of doing action A in a state S, I do the exponential of the parameter for that state and that action above. Maybe I can, here, okay, divided by the sum of all actions, like exponential term of a parameter for that other action and state. So the denominator is just there to make that the sum of all probabilities are equal to 1. The essential term is the term above. So since the probability has to be positive, this is an exponential, so it's fine. And it says that the probability of doing an action is basically proportional to the exponential of this weight. And we have only need to store and carry out one weight for each action. Okay. And so if you see, since each probability is proportional to e to the theta, then you divide by the sum of all actions e to the theta. So essentially the sum of all probabilities will add to 1. One thing which is helpful is that since these are exponential, what happens if, for example, I take all weights and I add the constant term to all weights? Essentially, here above you will have e to the theta plus a, which means e to the theta e to the a, it's a product. On the denominator, you will have the same thing, e to the other theta e to the a. So all the e to the a terms will cancel out. So if you add to the weight a constant term, the relative probability do not change. Okay, this is helpful sometimes because dealing with exponential can create problems, numerical problems. Okay, why it's called softmax? Well, it's a kind of you remember we used argmax. Argmax was very strict. He said, okay, the probability is 1 if you are the best. It's 0 whenever you are not doing anything which is the best. Here, actually, we are doing something soft. So it can happen that one action is very much preferred with respect to the others. So it will have a much larger weight with respect to the other. But still, each action will have a finite probability, even if extremely small. So it's a kind of softmax. And also, it's very important that it has a way to have always a finite. It can share probabilities in a very standard way. For example, if all weights are the same, then the probability is uniform. Okay, and the weights can be whatever they want. So actually, this policy can parameterize any finite distribution of probabilities. Okay. If you remember, in the policy gradient, we had two terms. The one is the Q value, or the estimator of the Q value. The second one was this scary terms, which was the gradient respect with theta of the logarithm of the policy of the action given the state and theta. So we want to show you that this is extremely simple to calculate explicitly for this softmax policy. So nabla theta is a vector of partial derivatives with a vector because for each term I have the partial derivative of one parameter, and I have many parameters for each state and action. So what is the derivative of the logarithm of a policy given an action and a state with respect to the parameters of a given action A and a given state S? Well, there are three cases. If the parameters correspond to that state, and the action corresponds to that action, this derivative of a logarithm turns out to be 1 minus the probability of taking that action in that state. Okay. So in a sense, when I take an action in a state, the derivative of log of the policy with respect of that parameter which corresponds to that action, that state, it's 1 minus pi. If the state is the one which I'm considering, but the action is not the one I'm using, so the action A over which I'm differentiating, it's not the action A which I actually considering, then this term here is minus pi. And if the state, so if I am considering parameters which do not correspond to that specific state there, the derivative is always 0. Okay, this is a simple result which comes out from having this form of a policy. Okay, it's not universal. It's something which shows us that using this policy is convenient, because something which may have scared before, this term here, actually we can write it down very easily. Okay, and again, I want to point out that these kind of policies have a natural way to end up into policies with finite probability for different actions, and stay there to converge to finite probabilities for different actions. For example, and it can be that there is a parameterization that I have two actions in which the action 1 is taken with probability 30%, and action 2 is taken with probability 70%. Okay, so when we dealt with before value approximation, this was not extremely important in the sense that we know that there was always an optimal action, or there could be ties in the optimal, so more than one optimal action, but then the probability was split between these actions. But since we have value approximation, it may well be that we are dealing with the case in which the best way, so to maximize this G, is actually to have finite probability. So this is actually a very important part of this software policies.
May I just add a small comment, side comment? So it's useful to think about these objects as eligibilities. That is, they give credit for what is happening to different parameters. Okay, so in the gradient, policy gradient algorithms, this means in this specific case, it means that if you just visited a state capital ST, you will not be giving credit, you will be giving credit 0 to all states, to all parameters that belong to states which are not the one that you visited. Okay, so this makes sense. You have many decisions to make over different states, but if you pick one, if you are in one state and something happens, you are not blaming other states. Okay, so this is typically what happens if you have if you don't have eligibility traces over time. On the other hand, what the first two equations are doing is that if you pick an action capital AT, then you're giving sort of credit with a plus sign, because 1 minus pi is positive to that action, and the negative credit to all other actions. Then the actual sign depends on the prefactor, that is the quality or the advantage. But this means to say that at the same time, if you pick an action, you're saying the action I pick will be credited proportionally to what I get, and the other actions will be the opposite. Okay, so what I didn't take gets the blame for not having been taken, and vice versa. Okay, so this is another way of interpreting these terms here.
Okay, so we were mentioning before that this simple result comes out only for the softmax policies, and clearly softmax policies are not everything there is in the world. One clear way which has been successfully used recently has been to use parameterization with neural network. So the policy is the direct output of the neural network. I'm just showing this, which is it's a very nice blog with a lot of also information, background, and also codes. It's let's say the idea it want to be a learning tool, but the direction is a bit more computer science than what we are dealing. So it's a bit technical, and everything is it's constructed in a way to be more efficient and less clear, at least in the code part. But if you want to see let's say the state of the art in using neural networks as parameterized policies and some tricks, I think that is a good way to see. But they will use many tools that we are dealing now with softmax policy. Okay, just to give you a reference of something which you may want to check out by yourself. Okay, so we have a way we know how to construct a gradient to follow. We know what is the parameterization we want to use for our policies. Now we want just to have a way to estimate this quality factor. So reinforce is considered it's always one of the first which has been treated in books and in reviews, because it's very simple. It does not need, it's an actor only, so it does not need to store and to estimate explicitly the value, because it uses Monte Carlo. So if you remember, Monte Carlo is just that instead of using or having to estimate of knowing the Q, we just consider this the return at time t, okay, the complete return at time t. So we will use this gradient of theta g. We will use this term which I've just analyzed and calculated explicitly for the softmax policies. And instead of using Q, we will substitute Q with the return for each time, the complete return. This has the same problems that normal Monte Carlo methods have. So to have the complete return, it means that you have already finished the episode. So this can be done only after an episode is finished. So you have to wait the whole time t to get there. And this can be extremely bad in the sense that sometimes the time t is very large. Sometimes you want to be able to bootstrap faster information. But still, this is a perfect legitimate way of doing things. Okay, so from now on it's extremely simple, because essentially this part here is the only new part in the algorithm, and everything else is just given by the fact that we are using, as we already used, a Monte Carlo way to estimate Q, which is the complete return. So the pseudocode is, as always, we have a new differential policy parameterization. So we are creating this softmax. So we are storing these parameters theta, which will give us the softmax. And then we are doing episodes. We are collecting trajectories. And at the end of the episode, we are calculating the returns, and we are doing the update following the rule given by the policy gradient. So you'll see without the last line, it was what we already used for value estimation evaluation for with Monte Carlo. Now we have this update of the policy at the end. So what new parts do we need? Very simple. We need two parts. We need a way to construct the softmax. So we need a way to store the theta. We have a way to call this policy from the theta and give us a random action and also the policy at the state. And then we need this way which comes from the policy gradient theorem to update the parameters every time the episode is done. Okay, so we need this to do one move with gradient ascent with this gradient. So as always, I'm using this auxiliary function which just does this discounted summation discounted returns, which is fun because I took it. I think I took it also from this spinning up OpenAI blog, and it was already written. It was written magic computing. I mean, this is just it's a very Python thing. It's in one line. You have no idea what happens, but in the end, you know that it works. So the class of reinforced, it's a very simple class. It's the same shape as always. We know that we need the space size and action size, a gamma, and the learning rate. Now the learning rate is not V because it's not for value functions, but it's for the action, the actor. Okay. But the idea is very simple. I need to save parameters for the policy. So I need to have theta. And remember that I have a different theta for each state and for each actions. And then let me go first to the actions. So when I have a state and I want to get an action, a single random action, what I have to do? I have to compute this. I have to take all the theta which correspond to that state. And the probability of doing an action is the exponential of that parameter theta divided by the sum for all the possible action in that state of the exponential of that parameters. Okay, this is the definition of a probability given by our softmax policy. As I said, a shift in the theta do not change the relative probability, but it's always useful to subtract this in the sense that if you have every theta equal 0, then the probability is uniform over the action. If you have every theta equal 1000, you have the same uniform probability. But when you try to ask to Python, do me an exponential of 1000, it says, okay, it's not a number. Okay, so this is a very stupid technical trick, which is mathematically exact but helpful in Python. Also, again, probabilities can go very, very close to 0 and which sometimes it's a mess. So I'm just doing that this clipping. It means that the relative distance between two values can be at most 40. And since e to the 40 is a number which is large enough, this is sufficient. So this is again a rounding error in a sense. Then this is the only interesting part. The probability of action, first you do the exponential of all actions, and then you divide it by the sum of all probabilities. Okay, this is the definition of the softmax. And then I'm taking an action randomly given these probabilities. Okay? This is a new thing which I added, but it's not even policy gradient. This is the definition of softmax. Then this is the second part, which is the same as before. I'm given a state, but I do the same exact step, but instead of returning a random action chosen by those probabilities, I return the whole set of probabilities for all actions in that state. Okay, but this is essentially, this is the softmax part. It's not the policy gradient reinforced part, which is even simpler. So all this model-free policy gradient reinforced method is here in these few lines and requires that you give it the trajectory of the state, so all the st plus 1, st plus 2, etc., all the rewards, okay, all the action that you took at the given time, And then, first of all, you calculate the return, the discounted cumulative sum of returns for each time, okay, this GDT at each time t. Then what I do here is I'm storing a way to compute only once the change in the policy, and then for all the different time steps, this is a way in which I just say that for every step I have 3 values. I have the time step, the state I was in, and the action I took. Then I'm asking what are the policy of doing the different action in where I was. And then for all the actions belonging to that state, and only for that state, because as Antonio was saying before, all other state, all probability of other states are not credited by this action. So this means just that for all other states, the change is 0. But in that state, all action will have an update. And an update is that if the action I really took was the same, is the one I'm considering, then the change is alpha GT for that step, 1 minus the policy. Okay, this is the estimator for the quality Q. This is derivative of a logarithm of the probability for the action I really took. Okay, if I'm considering an action act which I did not take, then I have this, I have the return, and I have minus the probability of taking. And then I just apply this change here. Okay. Okay. Okay, so essentially, can you see this all reinforce is here, and it's just in these 2 lines here. It's the way I am updating the parameters for the softmax with the return I got. Okay, do we have a question here? Otherwise, we can try and make it work. Okay, first of all, let's go in the same. This is, as always, the same trial loop which I'm doing. I have a number of episodes. I have this binning, which is the smart binning, which leaves us with only 6 possible states. This is the learning rate for the actor, and then I will do episodes, and inside the episode I will store the trajectories, and then I will store the performance, and at the end of each episode I'm going to do a single episode update, and then I will do many of them. One thing which is worth mentioning. Okay, so there are 2 different ways of dealing with discounted gamma. Okay, the one I'm using here is as such. Inside the return, so when I calculate the return here, when I'm calculating the return, I'm using gamma equal 1. Okay, so I am not doing a discount in the calculation of the return. Where is actually coming the gamma, which I want to put? The gamma is coming from the fact that I am asking, I am putting a forced end to the episode. Okay, so inside the discount, so inside the calculation of the return, I have 1, but each episode will last at most a value which I call time horizon, which has been taken from a geometric distribution of 1 minus gamma. This is effectively how the same that at each step I'm trying to kill the process by with a probability 1 minus gamma. Okay, what does it mean? So instead of putting the discount factor inside the calculation of the return, I am putting the discount factor inside the fact that my episode could die at any moment. Okay, it's an important fact. So if you do like this, so if you put an episode length which is stochastic and depends on the fact that you have a discount factor, then inside the calculation of the return, you have to put gamma equal 1. So calculate the undiscounted return. Why is it the same? Because you are calculating an undiscounted return, but you're truncating the summation somewhere. So either you do a discounted return, but then you have to take care of other things, or you do like this. So you do an undiscounted return, but the episode will deal at a certain point. Okay, this is the reason why I'm doing that. The time horizon is a stochastic number, and then I'm ending the episode at a certain point, which makes everything nice, because then instead of, do you remember last time the performance was the number which was how many steps it went? But now I can actually divide it with the number of steps by the time horizon. So I will get the number from 0 to 1. 0, it means that it has died immediately. 1, it means that it has reached the terminal state, not by falling down, but because it has stochastically terminated at some point. Okay, so then first of all, I want to show you this because I am not sure how long it's gonna take to redo the calculation. And this is, so you see now the performance is 0 to 1. And if we do a reinforce, we see that we have wild fluctuations, but on general, the policy seems to learn decently enough. Okay, but let's go through it. Okay. If you have a question about what I've already just said, please ask. So what I'm going to
make a question.
Yes, please.
What does this mean? This choice of gamma in the case of the Kert poll. That, for example, we are just looking at the effect of our action in the poll until a certain time, and what happened next, we don't care. Okay.
Let's say in this particular Kert poll example, the most logical way to do it would be with gamma equal 1. It means that we always care at an infinite horizon what is gonna happen. We want to find a policy which forever will keep it there. The problem is that if you do like that, the solution from those who created the environment, they say, okay, after 500 steps, you truncated it there. But because otherwise, if you find the perfect solution, there is no way to kill the episode will go on forever. Okay, so we are putting a time horizon, a limited time horizon, which actually does not have any sense in this particular case. Okay, let's say that also because there is no noise anywhere. The physics of the system are perfect. Let's say that we had a very small noise on the motion, then it could make sense to have a small a gamma close to 1, exactly for the reason you said. So in a sense, I'm saying, okay, I know where I start. I know that around here I should perform well, but I cannot be blamed for the accumulation of noise which happen, or for strange fluctuation that happens very far from now. Okay, in a sense. But you're right. In this case, I'm only putting a finite gamma less than 1 because I need the episode to stop somewhere. Otherwise, I cannot do reinforce, because the reinforce asks me to finish an episode, a total episode, before having an update, and if I manage to find the perfect policy, I will never finish that episode. Okay, I'm not sure.
Okay, thanks.
Thank you for the question. Okay, so let's try to run this. Clearly, I forgot to. Yes, because I put gamma equal. I have to. I apologize. Okay, let's say I put this. I apologize again. I always forget to. Okay. So this will go on for a while. And perhaps if you have no question, we can make a small break, and then after the break, we go on with the actor critique algorithm. Okay, then if you have no question, or even if you have, I will pause the recording now, and we will come back at in 10:15. Okay. Okay, I resume recording. So as you can see, the simulation has finished, and what we got at the end is this is the way that the
we cannot see the screen.
Ah, sorry. Yes, of course. Okay, sorry. So the simulation has finished in 1000 episodes. The result is such. So you can see this is actually even better than before. And so after a certain wild swings and variation and fluctuation of the performance, and then he has found a close to optimal solution, and then the majority of the reward are close to 1, the normalized reward. It means that it did not fall before the stochastic end of an episode. Okay, so one other thing I checked, we had by hand created our policy, which is 101010010101, so we can actually ask the reinforcement learning algorithm. So the reinforce, what is at the end of the learning process, what are the policies you have learned so far for this 6 state, and this is the result. So as you can see, while the optimal one is 1, 0, they have not yet converged, but still it's very close to 1, 0, it's very close to 1, 0, and very close to 1, 0, and then the last 3 are very close to 0, 1. Okay. And clearly this small fluctuation here are due to the fact that this still a bit far from being perfectly 1, 0. Okay, so this was the reinforce. So very, very small recap. We have policy gradient, we have actor only, so we want to deal directly with the policy. We have created policy with softmax, and we are using to update these parameters which parameterize the policy. We are using the return GT, which is the sum, the experience sum of all rewards of all the episode from that time to the end. So we have to wait for at the end of each episode. Okay, this is our basic view of this actor-only method. Clearly, this is very, very simple. You can always construct on this to have better performance, better ideas, better technical issues. Already, like with this, of course, I never deal with the fact that when you look at the learning parameters, it always seems that I'm putting random numbers. These are not random numbers. This is extremely delicate matter. So I always spend a lot of time to find a good range of learning rates. It means that, I mean, when you write some learning code, it will not work at first, and there can be two reasons. One is that there is an error in the code, and one is simply that you have not found the best tune to make it work. Most often it's both reasons, but even after you have dealt with the errors in the code, you still have to be very fine-tuning the thing. Okay, so we have found that Monte Carlo works. You need to wait until an episode, but at least in this simple case, it works. But what if I don't want to wait for an entire episode to end before making a single update? Then I need some way to do bootstrap. I need some way to extract information on the state, on the value of the state that we already have, and to put it into the estimation of the quality Q. In particular, we use what I called formulation tool from lecture 4. If you then you want to go back to value evaluation, but essentially the expectation value of Q is just the immediate reward plus the discounted V value of the following state when I start from a state and I act following the policy. Okay, so for actor critic, we need to estimate the quality. We will need to have some way to store and approximate and estimate also the value at the next state. And the information we have at a given time on this value will be bootstrapped into the information we need. Okay. We will use also a technique which has this helpful tool of the baseline. Okay, so the definition we had of the gradient was Q and then the gradient of the log of pi. However, if you subtract or add to Q any function of the state only, it means it cannot be a function of the action. If you put any function, can even depend on the state, then if you do the expected value, you actually find exactly the same thing. Why? It's a very simple calculation. What happens if I'm only considering the expected value of a function of the state and and the derivative of the log of the probability. Okay, the derivative of the log of the probability is the derivative of the probability divided by the probability. Okay, so we are doing the expected value of some function of S of the derivative of probability divided by probability. But the expected value is the sum of the probability of the derivative of probability divided by the probability. So you have the sum, the probability goes away with the probability. So you have the sum of some function with the state of the variation of the probability of doing the action A over all probability, over all action A. I apologize that I have not written down, but the idea is that if you put a function of a state, you end up, you do the calculation, and that small part there is just adding a sum of all action of the variation of the probability of taking that action. But we know that the sum of all probability has to be 1. So the sum of all the variation of the probability has to be 0. So any term which is a function of a state and not of the action, combined with the derivative of the log, actually gives 0 in the expected sense. Okay, why do I use it? Because actually this, if I use as a baseline the value for that state, I can do it because it does not depend on the action. We find something which is very familiar to us. We find something which is constructed as the reward plus gamma, the value of the new state, minus the value of the state where we are. And this, which is the new way we are going to estimate the quality instead of using the return, this is nothing else than the TD error. Okay, so reinforce, we have Monte Carlo approach. Now actor critic with this kind of chosen of baseline, we actually have essentially from Monte Carlo we have crossed over to TD error. Okay, good. Again, we need a way to approximate this value, and I don't touch anything from the last lecture. We're going to use this tabular value approximation with state aggregation, okay, which is exactly what, since we are using state aggregation like last lecture, now for each aggregated state, I'm collecting its value essentially, okay. I'm not doing the Q function, but I'm doing the value. So when in the last lecture, what I stored was of dimension state space multiplied by action space. Now I only need state space because I'm not storing the approximate Q function, I'm storing the approximate value, V. Okay, but the method and everything is essentially identical. What is the pseudocode? Again, I need a differentiable policy parameterization, which in our case is softmax. So given the data, I know how to construct a policy. A differentiable state value function approximation V, which in our case is this tabular, you remember the tabular way to go from an aggregated state to its value. We need two parameters of step size, one for the actor, which is this one, and one is for the critic. They need to be different, and then we have to talk a bit about them. Then I initialize the policy parameters, and I do episodes, and then, as always, I will end with a stochastic time horizon determined by gamma. And then until the state is not terminal, or I kill it, then I take an action, I do the action, I take a new state, I go into a new state, I take a reward, I construct my delta, my TD error in this way. I change with this TD error, I change my estimation of the values, so of the parameters which correspond to the values. And then using the same TD error and using this formulation here, I change my parameters which are constructing the policy. Then I'm a new state, so this I do at each step. Then a new step, new action, and so on and so forth. Now I can do at each step an update. Okay. However, now we have two separate things that are going parallel. We are trying to evaluate this line here, evaluate the value function, and we are trying to update our policy. Now, it's very important to understand that to create the correct estimation of the gradient, you need to have the best possible value for those states. Okay, because the change in the policy, the change in parameters relies in a heavy way by your approximation of the value. Okay, while the policy, the next step, so the policy actually its effect is instantaneous. You have a policy and you have a new action and you go away. So you need to be able to have the best value possible before changing the policy. Okay, so you have two time scales. A time scale in which you have to learn the value and a time scale in which you have to update the policy. And the time scale in which you learn the value should be much faster than the time scale in which you update the policy. Because the policy doesn't care. The policy, once you have a policy, automatically the next step is correctly done with the same probability dictated by the policy. But the value needs time to understand what is the value of the policy. Okay, so you have to have two different step size, and in general, you have that the step size related to the value learning should be much higher, in the sense that it has to be associated with a time scale which is much faster. Okay, two time scale, fast one related to the values, slower one related to learning policies. Okay. Good, then we go to the code. The code is, as always, a small implementation over the past code, which is rather simple. Now it has both ingredients. So it needs a learning rate for value, needs a learning rate for actor, needs to store the approximation weight for the value, which now are just a vector of the same size of the space size. And then you have to store the parameterization for the policy, which we know are as many parameters as the space multiplied by the action. Okay, then the single step update is super simple. We have to divide it into, we have first the critic update, and then we have the actor update. The critic update, we already know how to do it. The delta is equal to R, the instantaneous reward, plus 0 minus the value if we are done. And if we are not done, is R plus discounted future value minus our value. Okay, this is as always. Then I update the value for the state I'm in using the corresponding learning rate multiplied by the delta. Okay, so this delta is the normal TD error. Then the actor update is super simple again. Essentially, it's the same as before. I now have a delta. I construct the policy from the state I'm in for all the action in that state, because remember, all action corresponding to other state have a 0 update. I loop into all actions in that state. If I actually did that action there, then that update is learning rate delta 1 minus policy. If I did not do that action, the update is learning rate delta minus policy. Okay, this is the normal softmax term. Okay, this is, as always, nabla theta log pi. Okay, this is that term there. This is my delta, which corresponds to the quality factor, and this is just my learning rate. Actions are created as a softmax, so this is literally copy-pasted by above. Policy is literally copy-pasted by above. Then something will fail. And then I'm going to do actor critic. Everything is the same. I have the same binning. I have 2000 episodes. I don't know why 2000. I have the learning rates. Now you can see that I put two different learning rates. Again, took me a while to find two numbers which did not find stupid solutions. And you can see that one is almost 10 times the other. It means that the learning process for the value is 10 times faster, in a sense, for the learning rate for the actor. Again, I create an actor critic, blim, blim, blam, the same as before. I do the episode. 2000 is a lot, and I will show what actually turned out. This is the same as before. If you have questions, please stop me, but this is exactly as before. I just using a different algorithm. And you can see I done already 2000 episodes. At the end, this is what I find. The policy optimal is 1.0. I found very close to 1.0. The first three are almost all 1.0 with less than 1% of error. Also in the other three. And indeed, the result is that I have a very nice, stable solution, almost optimal. So from 500 episodes afterwards, almost all episodes end up not because my poll has fallen, but because time has run out. Okay. I hope you can appreciate that actor critic is very simple. It's just the same. I need to have an estimator of this quality Q. How can I do it? I do bootstrapping. How? How I learned the last time during value estimation. Now we have something new, which is a bit different, a bit complex, but actually without other names, most of the nice result and new application and algorithms stem. Please.
Yeah, I have a question regarding the previous part where you said if your code doesn't work, it's either there is error on your code or there is problem with the learning parameter or the learning coefficient. So what would be a good or efficient way to tune that parameter, especially that sometimes it takes a long time to run all the episodes. So it will be a little bit hard to find the right parameter or the right range.
So normally speaking, the best thing is doing an empirical thing. So for example, if you can scale your system, it's if you're able to start with the smallest problem or with the simplest problem and then try to see. Second thing, one thing you want to check, for example, is you can store how the value and how the policy change in time, and you can plot them in time. And then it's very clear if the policy are changing fast and the value are constant, it usually means that the value are not changing at all. So generally speaking, I will do, let's say you don't need to arrive to convergence. You do the smallest system as possible. You do only a fraction of the time, and you try to keep the trajectory of values and policies. And what you want to see is that values change and perhaps arrive to a convergence, and then only the policies change at least slower than the values. It's not simple to do that, but I think that this is something which you have to do in a sense by eye. There is of course one meaning. I mean, you know that the learning rate essentially gives us a scale. Okay, learning rate of 1, it means that whatever I just learned, I forget and I replace it. So a learning rate of 0.01, it means that I have 100 cycles of learning to replace my old information. So that gives you a scale of how many steps do you think are sufficient to properly estimate something. Okay, so for example, let's say that I know that for evaluation I need to have 3,000 steps of policy. Then my value learning rate should be smaller than 1/3,000, because I need to average, in a sense, all these 3,000 steps in which different things happen. Then I know that my policy should be smaller than that. Okay, so learning rate correspond to a time scale if you just invert them, in a sense, and you always want to plot them and to see what happens. Normally speaking, if you have a too large learning rate for value, for example, it will fluctuate a lot, and you don't want to fluctuate. You want something which can fluctuate, but it should be smoothly fluctuating, in a sense. These are very empirical things. I think that I do not have a perfect answer to that, but those two ingredients, checking in trajectories and doing roughly mathematical sense, in the sense how many steps do you think needs to properly sample, those two can be helpful. Okay, so let's try to put everybody to sleep with this part on the natural gradient. So natural gradient is hard topic, but it's very nice. So the idea, and I will reiterate something which you have seen many times with Professor Celani, which is what are we doing when we are doing a gradient update? So with policy gradient methods, we are changing the parameters theta, which are those which define the policy, by a small amount in the direction indicated by gradient. What do we mean by small amount? We mean that in general, when we have a function and we're trying to change the variable x such that the new update is the old one minus or plus some term of a gradient, it means that we are doing a minimization not in the true function f, but in an approximation of f, in a local approximation, which uses the only thing that we know. So the approximation of the function in x uses the fact that I know the derivative of the function in xt. So this is a basic, in a sense, a Taylor expansion of the first part. So this is just that I know that if I move away from the place I'm in, I move in this gradient, but I also penalize the fact that I move by a squared distance between where I'm going to end up to the end. So this, if I try to minimize this or maximize this, it's a follow the gradient. The second term means don't go far. Okay, this is like your parents saying go in the garden to play, but don't go too far. Okay, this is go to the garden to play, I want to be alone. You shout too much, and this is please don't go over the state because a truck will get you. Okay, so this means in a sense that we are trusting the evaluated gradient, but we are not trusting too much, and so we are saying to stay close. The problem is that we are saying to be close in a distance with respect of x, which may not be the good thing. So this is the worst drawing you will ever see. And essentially it's like it's a function map. So this is a minimum or a maximum, I don't care. And this is the point where we are, we have the gradient. Now you can see that you can move in x in two directions, but not all directions are equal. So if you move in x in this direction here, the function changes a lot. Okay, so that function there, with that direction there, is both a good direction in the sense it changes a lot, but also a dangerous direction. Because if the function changes a lot, then nobody tells me that my gradient will stay the same in that direction. But then in this direction here, the function changes very small. So both I mean, if I move there, my distance will be the same, but actually the function will not change it by much. And also my estimation of the gradient should not change by much. Okay. So in a sense, we are here in the space of a policy. We have this, let's say that this is the probability of taking probability A, and this is my theta. Okay. The probability of taking action 1, and this is my theta. So I don't care about the parameters theta, because the parameters theta do not mean anything. What is the true meaning is the probability of taking an action. If I change, for example, if I change all my theta by a constant amount, we have seen that the policy are the same, but it costs a lot in distance. But I don't care, that price there, I am willing to pay, okay? I don't care to change my theta if the policy does not change. So this means that instead of having to pay a price which is proportional to the distance in the parameter space theta, which I don't care because I don't care about theta, I want to pay a price which corresponds to the distance in policy space, in a sense. Okay, so I move theta, but since what I really care is the policy and everything depends on the policy, I know that if I move, but the policy stays close, stay relatively close, then even the gradient which I have estimated will not be wrong too much. Okay, so I want to move in the direction in which the policy change and not in which the parameters change. Can you see what I mean? In a sense, we want to move as quickly as possible in the direction where policies do not change, but move with caution in the direction where policies change fast. Okay. Since I have a local approximation, I want to that my local approximation, I want to move along my local approximation, but not too much. I don't want the gradient to be too wrong. And the gradient will be wrong if I move where my policy will be very different. Okay. It turns out that there is a way, a mathematical way at first order to achieve this, so that instead of a gradient, which is the immediate direction of falling, we have this natural gradient, which is the inverse of the matrix multiplied by the gradient. The Fissure matrix, which is this matrix here, is defined as such. It's defined, so let's say I have a vector of parameters, and we do have vector parameters. In our case, our policy is θ1, θ2, no? It's a list of theta. Then each element of that matrix is the sum of the probability of taking an action for each action, of the derivative of taking that action, of derivative respect of 1 theta, theta I, of the logarithm of taking that probability, or taking that action, I apologize, multiplied by the derivative of the logarithm of taking that action by the parameter theta j. Okay, so the Fissure matrix associated to a policy pi is the expected value expected in the action of the derivative of the logarithm of the probability of this policy by a parameter I, and derivative of the logarithm of taking that action by the parameter j. Okay, this is a single element of this f theta, which enters here. Okay, what I want to, first of all, I want to, this passage here we will try to clarify, but I want to point out that if instead of theta, of gradient normally, we follow the natural gradient, we are able to move in the direction not in which I'm penalizing for theta to be different from where they were, but I'm penalizing the policy to be different from where it was. Okay, doing this change here shift our focus of the penalization from I don't want my parameters to be too far, to I don't want my policies to be changed too much. This is the idea without the mathematical detail. Mathematical detail is that once I have a policy, the Fissure matrix associated to the policy is such this. Okay, this is generally whenever I have a probability distribution over a variable a, the expected value, so the sum of the a of the probability of a of the derivative of the logarithm of the probability over a parameter and derivative of the logarithm of the probability for another parameter gives me a Fissure matrix. Once you have here, still you have no idea what to do with the gradient, okay, natural gradient. But now we will show that there is, for softmax, there is an extremely simple expression for this natural gradient, okay? Only in this case, but in this case we will have it. How does it work in practice? So remember that we have a policy which is parameterized by these n parameters, θ1, θ2, θn, okay, which correspond to each state, to each action. Let's forget about the state. So we are in one state and we only have one theta for each action. Okay, we have an action 2, and we have theta 1, theta 2, etc., etc. Then we know that the policy of taking that action given that theta, it's, which I will write pi of a, it's the exponential of that, of a relative parameter theta divided by the sum of over j, over all possible actions, e to the theta j, okay? And also we already know what is the standard gradient of this policy, because we know that the, I apologize, here, okay. You can clearly see that here I forgot a log, please. Please, if you're writing down, please, I have no idea where I am. Let us recall. Yes, okay, I found it. I apologize. Okay, I know how to deal with it, because we already saw that it's, if I have the probability of taking an action and I do the differentiation by the parameters, it's either 1 minus pi, the probability of taking the action I, or it's the minus the probability of taking I, whether, depending on the fact that the action I is the action I'm considering or not. Okay, we can write in a more concise way, so that this the log pi the theta I equal to 1. This means 1, but only if a equal to I, minus pi I. Okay, now we can construct mathematically the Fissure information matrix. Okay, the element ij is, this is the first line is the definition. The definition is sum of all possible actions, probability of taking that action, the log pi the theta I, the log pi the theta j. But we have just seen that single one of these is 1 if it corresponds to this line here. Okay, so just replacing this line here, we have this sum of all possible action, the probability of taking an action, this term 1, but only if a is equal I, minus pi I, and then 1, but only if a equal j, minus pi j. Then this is a product of two terms, so there are actually 4 terms. Then if you do this calculation here, which is very simple. Why it's simple? Because you always know that if a sum over a pi a stays, it sums up to 1. Okay, so actually it's very simple to deal with it. So from this, only 2 terms survive in the end. Okay, please, it's very simple to do this calculation. The calculation leads to, I have pi I, but only if I am in the diagonal. So if j equal to I, j I are the position in the matrix, minus policy j, policy I. Okay, this is the end. So I calculated each entry of a Fissure matrix. But I do not need the Fissure matrix. The natural gradient comes with the inverse. Okay, actually we can do it. It's one more step, but we can do it. So we wrote the natural gradient as the inverse of the Fissure matrix for the gradient. But clearly we can also write the Fissure matrix applied to the natural gradient, and this is equal to the gradient. Okay, I just applied from the left the Fissure matrix, and here I have an f coming from before, from left. Here I have an f, but f minus 1 cancel out. Okay, so let's write this expression here explicitly. And in particular, since this is a vectorial expression, I take only one term. Okay, I say this is matrix vector. I take only one term. So if on the right I take the term I, so I'm the over the theta I. So this is the standard gradient over parameter I. What I have on the left, Okay, do you have questions? How many questions do you have? Okay, let's just go to what happened. Okay, we essentially have found that if we want to go away from we want to follow the natural gradient, we have to determine this new natural gradient. There is a way to express it in this way. So the old gradient, so the standard gradient, is associated to this term here. So it's a matrix product. So if I want to determine element I have to sum over j of the matrix element j and over element j here. Now we know that we want to apply it to the logarithm of the policy, because this is our end goal. So we plug it here. So we applied all this term here to the logarithm, all this term here to the logarithm, and we separate the two. On the right, we already know what is the solution of this. If I do the derivative of the logarithm of the policy, I have 1 minus pi. On the left, I know how to write the Fissure matrix element ij, so I end up with this term here. So the point is that since I have this equation here, I can find out what are the natural gradient j of the logarithm, because I have everything else. Okay, this is an equation in terms, and once I solve them on terms, I say, okay, for this equation to be correct, I need that this term in parentheses here needs to be 1 over pi, but only if the action is actually the action I'm considering. Okay, this means that if I want to move in the parameter space with a natural gradient, I will change the parameters of only the action I really took. This is the meaning of 1a equal j, with a weight which goes inversely with the policy. So this weight, if the policy is close to 1, this weight is 1. So it does change not much. But if a weight is very, very small, if the probability is very, very small, then the update will have a weight which could be infinitely large. Okay, so the natural gradient says, if you are in a region where your probability is very small and I want to change that, I will make an incredibly large change so that I actually modify the policy. Okay, and this makes sense because, again, we want a change which does not care about how much the parameter change, but cares about my policy change. And if my policy is very close to 0, to make it relevant, I have to add a very large update. Okay, but what we care is that in general, this was a solution which gave us explicit solution for the derivative natural gradient of a logarithm of a pi, which is used in the policy gradient. We have an expression, which is an analytic expression, but only for softmax policies. What happens when we do not have softmax? It's a mess. Okay, can be solved iteratively, it can be approximated and everything, but it's not this clear. This is what I wanted to briefly show. So here in this blog, which is very nice, there's a lot of equations, but it's written to explain. It's not written to be used in technical sense. And you can see that here is vanilla policy gradient, which is what we used, actor critic. Then you can see this trust region policy optimization, proximal policy optimization. These are not exactly a natural gradient, but are in the same sense. So trust region, it means I'm trying to move, but where I trust my gradient, okay? So they are all ideas which are extremely state-of-the-art idea, which employ the fact that we do not want to move in parameter space theta, penalizing moving theta, but we want to move trying not to change too much the policy, which is exactly what the natural gradient does in a sense. Okay, finally, the class actor critic. This is, I just need 10 seconds because it's literally the same thing as before, except that instead of having the loop of the action and then one minus policy or minus policy, I have one single update only for the action I really took, and the update is the value, the quality, divided by the policy. Okay, so everything I said here, you can forget, you can just remember that the new, instead of the derivative of the logarithm of the policy, which was 1 minus policy of policy, which you have here, instead of having this line here, we have this line here. That's it. This is the natural gradient for softmax policies, okay, which correspond to this line here. A very small technical thing. Why do I have this term here? Simply because we have seen that the policy can be very close to 0. So a single update can be incredibly high. And this makes so that the variance can be overwhelming in this algorithm, okay? Because if policy is 10 to minus 20, and I have an update which is 10 to 20, then everything becomes not a number, and so usually there is this technical fact that you put a cutoff so that you know that the update is at most the inverse of this number here. Okay, but this was just a technical issue. Okay, this was actor critic with a natural gradient, and you can see that it learns. Okay, I will not do it. So it's, again, I apologize, but it's the same as always. So doing episodes, I'm creating the binning, I'm creating the algorithm. You can see whatever I've done, but I've done exactly the same as before. There is only one line which has changed, and the performance is such. And you can see that now performance is actually 1001. Okay, it's as found, it's a much faster convergence, and indeed it's basically always optimal. Okay, and the good thing is that even if these numbers here are very, very close to 0 and very close to 1, if something changed in the environment, the natural gradient would be able to change them back to other numbers. It's not stuck there because it has a way to escape from probability 0 much faster than any other algorithm. Okay, this is last thing I wanted to say. If you have questions, please ask. But we are running late, so I perfectly understand if you want to close the class here.
I want to ask about the natural gradient.
Yes, sure.
So what else are the other natural gradients?
Okay. So the natural, you mean what happens to the natural gradient if we are not using a softmax policy?
Yeah.
Okay. There are very complicated way to keep track of things. Okay. Now we have an explicit way that we know that the natural gradient for this particular case is exactly some value. Normally, one has to store an approximation of this function inverse matrix, and you have, at each step, you have some iterative calculation which allows you to get a closer approximation of this inverse matrix, and then you apply it. So instead, here we managed to have the natural gradient perfectly designed, perfectly expressed, and using directly. Normally, it means that you have something like an eligibility trace. You have new parameters, which helps for a new approximation, and you use this new approximation inside a code, and you have at each step a new update also for the Fissure matrix. This is how normally to deal with natural gradient if you do not have a closed expression for it. For that reason, they learned that there were better ways, simpler ways, for example, to deal with natural gradient. For example, there is a very simple way, which is clearly not elegant, which is clearly mathematically has no proof of convergence, but it has been proven to work well under certain cases, which is called PPO, clipped. It's very stupid. I can tell you in a second. So you do standard gradient, but when you keep your policy. If your policy has changed for more than 10%, you put the gradient to 0. Okay, which does not clearly find the natural gradient, follows the natural gradient, etc., etc. But it helps in the same way that says, do whatever you want, but don't move your policy more than 10%. Okay, in a sense, it's doing what the Kullback-Leibler distance is doing mathematically, but it's doing in a very crude way. Okay, so that is a new kind of algorithm. You can find it here in PPO. So you see, it says instead, look, do this minimization of this minimum here. This minimum here basically says, it says if your policy over the old policy is different, more different than 10%, kill it. Okay, so it's not clear from this picture alone, but it's in a sense of what can I do if natural gradient is not available as a closed formula. Okay, I apologize, I answered too long. I hope that something was answered.
Yeah, I understand. Okay. Thank you.
So if you have more questions, I will first stop recording.